whenever I talk to people about this, everybody has a slightly different viewpoint on what a software build system is. So I'll give you my definition, which is a rather academic one, but it separates it from all the other definitions. I'll talk about some of the common build tools that exist in the industry, and you've probably heard of many of these tools, but I want to talk about some of the pros and cons. Because I think my observation of the industry in general is that people are using tools that are not really suitable for what they want. So I'll talk about that a little bit. The main bulk of what I'll talk about is the challenges. Okay, so what are the challenges that people see when they have poor quality build systems? Okay, and I'll talk about, because we're all management people, I'll talk about dollars. How many dollars do we waste by using poor quality software build systems? That's a really key takeaway from today. And finally, I'll talk about recommendations. I've only got like 20, 25 minutes to do this, so I can only cover 3 recommendations. I do have 600 pages of other recommendations if you're interested, and I'm around until the end of tomorrow, so you're very welcome to come. I'd love to chat with you. I love learning about people's build systems and how they do things and the problems they have. So firstly, let's go and define what a software build system is. So I'm a programmer by nature, so I think about a software build system in terms of source files. So this is in the C programming language. Imagine I have a program here, has 3 C source files, one called graphics.c, one called security.c, and one called math.c. Hypothetical program. Each one of these source files, if you're a C programmer, you'll know this, can include header files. A header file contains type definitions, constant definitions, and so on. But the important thing here is that these C files depend on the content of math.h. There's a dependency. That's the word you'll hear a lot. So my software build system, in my terminology, is something has to translate this source code into object files, which the computer can understand. Now, in C language, you have .o files, which are object files. Anybody who's programmed in C will know this. This is really obvious. So I need to do the same for security.c and also for math.c. OK, until I can actually execute this, I need to actually link it together. So that's the final step. OK, so anybody who is a programmer, this is really bread and butter stuff. If you're a manager, this is sort of stuff you should know that your teams do. It's very fundamental work. OK, so this is what's called a full build. Okay? Now, if I'm a developer and I go and modify math.c, okay, I fix a bug. I change one file. Okay? I want my build system to then go and recompile only those files that I want to have recompiled, which is math.o and myprog.o. Hold on. There we go. Fundamental as well. That's called an incremental build. Now, that's fairly simple concepts, but in reality, it's a lot more complex than that. In reality, you have enormous software, millions of lines of code. How often does it actually work like this? Not often at all. How often does it fail and cause you grief all over the place? Quite often, right? And this is why I'm talking about. This is why I've studied this for such a long time, because it's really not as easy as that. There are so many things in your software build system that cause grief because these dependencies are broken. And I'll talk about that shortly. OK, the one thing I want to clarify, there's always a lot of discussion about continuous integration and continuous deployment. Wonderful. We talked about it. It's an excellent thing. But from my perspective, that's not the build system. That's sort of a management layer. I call that build management on top of this build system. So continuous integration is checking out the code, compiling the code, which is what I talk about mostly, deploying it to the machines, testing it, and reporting on the results. So to me, the build system is the top part. It's not the bottom part. And I just say this because, just to clarify, make sure we're all thinking the same way. OK. So when I look at build systems as well, I look at the different aspects of the industry. Now, I know there's a lot of people here who do what we basically call websites, basically massive websites, obviously. I come from a background which is more in embedded systems. So I'm a C programmer originally. I worked on routers, operating systems, and devices. I've done all sorts of really low-level stuff, touching the hardware of machines, touching the hardware of custom devices. In that world, you care about high performance. You care about everything happening as quickly as it can possibly happen. People who write routers would not consider using Java. I'm stating the obvious here, right? It's 10 times slower. Why would you do that? So in this environment, you are very aware of the compilation process. I'm a developer. I'm typing in code. I have to go in. I have to kick off a build. I have to wait for it to compile the C file, to create .o file, to link it to an executable. I have to sit there and wait. And that's the key message you'll hear me say a lot. I have to sit there and wait. Okay, it's a productivity problem. So this is one very big segment of the industry. And if you look at, I think every year they publish a list of all the different programming languages that are used. It used to be Fortran and COBOL were the most common languages. These days it's C. C and Java are usually number 1 and 2 on that list. So there's an enormous segment of the industry who use C programming. Although many of us think it's very outdated, it is actually still very, very common. So this big full compilation of source code is a very big part of our industry. So the next segment, that is probably where many of you are in, is the sort of Java, C#, .NET environment where you're building business applications, user interfaces, those sorts of things. Now in this case, yes, you still do have an upfront build. You still have source code, you still have class files in the Java terminology. You still have to, you type in your code, you have to do some amount of build before you can run your code. Now in Java in particular, now I'm an Eclipse programmer, so I use that all the time. I am very used to the concept of typing code, hitting save, and I know instantly that Eclipse is going to build that for me. I can hit the run button right away because it just compiled the one file that I changed and it's ready to go. And that works because of the way that Java works. I can dynamically load in new classes whenever I want. It's a wonderful feature. So in this segment of the industry, there is still some building, compiling aspect to it, and there's still some waiting before we can actually do it, but it's much, much shorter than it is in the C environment. Now, not to leave anybody out, of course, is the web and the scripting world. In web development, you don't often have that pre-compile step. Because if you're writing JavaScript, or if you're writing PHP, what do? Well, you save the file, and then you reload the program into your browser. It automatically, implicitly compiles because it's really interpreted. Okay? So you don't necessarily have a pre-build step where you sit and wait for it to compile. Now, having said that, I know a lot of you are in this industry and you say, well, yeah, I do a lot of packaging and translation of images and all that sort of stuff. Yeah, there often is some sort of step, but it's typically not what the developer does and sit there all day long. So if I look at the most challenging environments, it's the left-hand side, the router industry, the operating system, the devices. I come from a background where you can sit for 25 minutes, half an hour, waiting for something to compile before you can test it. The middle industry, it's not quite as significant, but there is still a build step where the developers sit there, unproductively sit and wait and do nothing. Okay? So that's just to put things in perspective, why I think software build is an issue that we need to think about. So let's look at history. Almost everybody who has ever written code has heard of the program Make. Okay, Make was invented, I think, 1977. I'll give you an example right now. This is the exciting code you're going to get to see. And basically, it is 40 years old, and it is still one of the most common build tools in existence. Okay, here is the exciting code. Everybody awake? Woohoo. Okay, so what this is telling you, this is a textual representation of the graph that I showed you on the previous slides. I'll just go through it briefly. So on the top line, we're saying graphics.o is a file that is generated from graphics.o and math.h. To generate it, I have to run it through the C compiler with using that command line. The next section is exactly the same, except it's for security.o, then math.o, exactly the same, and the bottom two lines is when it actually links it all together and makes an executable program. So regardless of whether you're a programmer or not, this should be fairly straightforward. On the left-hand side is what I'm trying to generate. On the right-hand side is what it's generated from, and here's the command that does it. Now, this was great in the 1970s. It was a wonderful invention. It won lots of awards, and I'm being genuine when I say that. But you know, in the 1970s, we didn't have big software. Now we have software with tens of thousands of lines of code. I can't possibly write this out 10,000 times. That's ridiculous. You might also notice that, you know, why have I got math.h there? Shouldn't it automatically figure out for me that I'm including math.h? Well, yeah, I don't want to have to tell it. I've got 10,000 source files, and I don't know how many include files. Why on earth would I do that? You look at the last lines. I list graphics.o, security.o, math.o. And then I list it again on the next line. That doesn't make a lot of sense, does it? So clearly, this simple model that was so wonderful in the 1970s doesn't scale. So let's look at an optimized version. Okay, that make a lot of sense? I should buy you a chocolate bar if you can understand this, because, honestly, I have a hard time understanding it. The point is, to optimize it, and this does all sorts of clever things to automatically simplify it and make it shorter and make it automatic. It's not easy. And the message I'm trying to say here is that Make is not the right tool for us because it's complex. Now, I worked on a project a few years ago where there was somebody who had worked for 2 years, very expensive pay rate for 2 years, creating a wonderful, new, amazing build environment. He rolled it out and said, hey, everybody, here it is. Everybody looked at it and said, huh? Didn't understand it. Nobody except for him could actually maintain it. Obviously, that's a business risk. Why on earth would we do that? So we backed it out and said, sorry, you know what? We wasted the money. We cannot possibly take your amazing solution. And this guy took several days every time we needed to fix a bug because it was so complex. He was the only one who could understand it, but it took him 3 days to fix a bug. Why on earth would we invest in that?